Now in this video, this is gonna be in my opinion, it's a pretty exciting topic. It's because until now we have been dealing with op amps which do actually we've been dealing with amplifier circuits which do arithmetic operations, right? Like addition, or inversing a signal, or basically amplification, multiplying by a constant, um, finding the difference, etc. So we have only been dealing with arithmetic operations so far. Today we are going to look at an op-amp circuit which can actually differentiate, which can actually find the derivative of a voltage signal. So it's pretty exciting. So let me draw the circuit, and what the circuit is actually basically something like this. So you take your inverting op-amp circuit, you take your inverting amplifier. Okay, so let me draw the circuit for that. Okay, I'll leave a gap here and you'll definitely know why in a bit. So I'll leave a gap here. It's basically your inverting amplifier circuit. You have your op-amp here. This is the negative, this is the positive. You have you have a feedback resistance here, your negative feedback resistance. I'll just call it R for now because, well, again, you'll see in a bit why I don't have to put a subscript F there. It's just let's see. And we have the negative input right here, negative terminal right here for the output, and this is our output voltage, that's our supply. Let's say this is the ground. All right, so this is the ground. So okay, why did I leave a gap there, and why didn't I put a subscript there and all that? So the thing is, your differentiator, as I'm saying, this is going to be an op-amp which can differentiate. Pretty cool. But the thing is, just using our basic resistors, okay, in the external circuit, around the op-amp, you can actually not achieve something like this, very unfortunately. And we actually need a capacitor here. Okay, that's the only difference from an inverting amplifier. Take your inverting amplifier circuit, exactly the same thing, but you instead put a capacitor here. So capacitor of, let's say, capacitance C. Okay, so this is your differentiator circuit. And also I think you can see why I didn't put an F there, because this is the only resistor. That's why we don't need to you could say differentiate between resistors. That's an unintended pun. But anyways, yeah, so this is your circuit. Now obviously I haven't shown exactly how, or actually the fact that it even does differentiate anything, okay, or does something meaningful for us. So let's actually prove that. Okay, let's actually prove that. So we know that we are dealing with an ideal op amp. Okay, so we're dealing with an ideal op amp. So this is 0. This is this whole node is the ground, so this is gonna be 0 volts. All right, now if that is 0 volts, this is also gonna be 0 volts. And also the current here, here in the inverting input, going towards that, is 0. All right, now we have a current here. Okay, I'll call that I sub C, the current entering the capacitor, and we have a current here. The current that's I'll choose a different color for that. So that's the current that's exiting. The resistor. That was a bit too light. Anyway, so I'll call that I sub R. Okay, so we can set up, we can apply KCL here on this node. Okay, we can set up an equation. So the current entering is equal to this current that's exiting. This is 0. We don't have to care about that. So let's actually set up our equation. First, I'll deal with first, let's see. I'll just write this for now. So I sub R equals it's a bit tedious to keep switching colors over and over again. Okay, so I sub R is equal to your I sub C. Okay, now your I sub R, that's pretty easy to find. What's your in this direction, you could say, or and the polarity being in this direction, what's your voltage difference? Okay, and it's you'll see why I'm mentioning the polarity and all, because we really need to be careful with the capacitor for that. But anyways, the resistor is pretty simple. So it's 0 minus, well, this is V naught right here, right? This is V naught right here. Well, not V naught, V output. 0 minus V output divided by R, right? Well, divided by R gives you your current. So your current is gonna be your potential difference. That's 0 minus V output divided by your resistance R. This is gonna equal your capacitor current. Okay. For this one, we just need to be a bit careful. First time I was studying this basic capacitors, I always got confused with the current direction, the polarity, etc. It's pretty simple. Your current, okay, so if your polarity is like this, okay, if your polarity like this, so is like this, so this is Vs, okay, this is Vs, this is 0 volts. So we have our polarity like this. This is Vs right here. The way to find your current, okay, if your current is in the same direction, you could say as your polarity, okay, like this, so it's gonna be given by your let's see, the capacitor current equation. Actually, I haven't made any videos on capacitors and insulators on the date I'm recording this video. Hopefully in the future I will, hopefully. So here what you will have, your capacitor current is basically gonna equal your capacitance, okay, multiplied by your potential difference, okay, multiplied by your potential difference. All right. So, and well, the thing, as saying about being confused and all, I always thought, do I put a negative in front of this or not? And the answer to that is always, just take the current in the direction of your potential difference. Okay, that way you wouldn't have to put a negative in the formula itself. You might have to do it if you're using KCL for some purpose, but this reduces the confusion a lot, for me at least, if I don't have to worry about negatives in the formula for the current here. Anyways, that aside, it's not really the topic of this video. We're almost done, right? We just need to make this the subject. So your V output is gonna equal negative of your resistance, so minus R C, the derivative of your supply voltage with respect to time. So we are done. So as you can see, two things here. First thing, obviously, we lo and behold, we have the formula, and the second thing is, that's the most important thing for this video, is that it does in fact differentiate. Okay, we are in fact finding the derivative of our supply signal, the time derivative in fact. So it does in fact, the name does just does justice to the structure and the formula. But anyways, yeah, so, and you might have noticed another really important thing. What is R into C? What is your resistance into your capacitance? That's basically the time constant, right? That's basically your time constant. So you can also write it like this. Okay, you can also write it like your output voltage is gonna equal the time constant multiplied by the derivative of your supply signal. Okay, so that is another way to write this. Pretty neat. Okay, but we haven't seen the cool things it can do yet. Let's actually jump right into some. Actually, before doing things numerically, I'd actually like to do things a bit more visually for now. So well, one thing is, although the diagram doesn't make it look so, it is, let's just say it is symmetric in the sense, you know what I mean, the amplitude being the same and all. Anyways, and the time intervals here too. So this is your supply signal. This is your supply signal. Now, what I want to know is, if I just feed this to my differentiator, this differentiator that we just saw, what am I going to get? What am I, what's my output going to look like? What's my output going to look like? Okay, this is pretty interesting. So this is gonna convert your supply signal to some output, right? We don't know yet how it's gonna look. So let's actually draw a set of axes. How is it gonna look like? Well, one thing is we always, and this is something we really need to be careful about. Well, actually, this really comes from the differentiator. You could say is kind of like a child, or kind of like it came from the inverting amplifier. Okay, and as a result, just like with the inverting amplifier, although the name there makes it pretty simple to realize, not here though. We really need to be careful about the negative sign right here. We really need to be careful about that. Okay, so with that being said, what happens here? Okay, ignoring the magnitudes and all for now, this is just some, this is RC, the time constant is just some scaling factor. Okay, it's just some positive scaling factor. What happens here is, okay, so you take the derivative of your supply and you make it negative. You take the derivative of your supply signal and you make it negative. That should at the very least give us the shape. Okay, that's what I'm gunning for right now. So if we try to do that, so suppose say this part right here, this part right here. Okay, if I take the derivative of that, it's some constant positive value, right? Some constant positive value, the slope. And if I negate that, what I'm gonna have is some constant negative value, right? What I'm gonna have is some constant negative value like this. So I'll try to draw it as small as possible here. So this is gonna be this part. Okay, this part is gonna give you this in the output. Okay, let's move on. Then you have this part. Then you have this part, right? And this is the derivative of that is going to be some constant negative value, right? Some constant negative value. And if you take, if you negate that, you're going to get some constant positive value. Okay, so I'll draw that right in. I'll draw that right in. So you're going to have some constant positive you're going to have some constant positive value right here. The time intervals, I don't think it's matching, but it should be double of what it was here. Yeah, I really hope you guys really don't mind these things. Okay, so and last but not least, same logic as in here, except different, the opposite case. Okay, it's gonna be the result's gonna be a constant negative value. Okay, I think you can see it's kind of like alternating, right? It's alternating the signs. So it's gonna go out of the axis. Yeah, it looks at least decent. I wouldn't say it looks good, but yeah, this is how your output signal is gonna look like. But this is pretty interesting. Okay, I'll just draw in these lines so that it's you can see this much more clearly. But what did we just do? I mean, actually, not we. What did the differentiator just do? Well, it took one waveform, okay, specifically this triangular waveform, this was our supply or input, and it basically changed the waveform itself, right? It basically gave you an output and changed the waveform. Okay, that's pretty fascinating, and it's also not something that the other op amps that we have studied so far, it's not something that those could have done. Okay, those can amplify, those can invert, those can phase shift and all even, but they cannot do something like this. They cannot change the shape of the waveform itself. So it's pretty fascinating. It's pretty fascinating that what we have just obtained from the differentiator. All right, so since we have seen what it does here, actually I'll encourage you to do one thing. Try to do the two things actually. One thing is, if you pass this, suppose say if you pass this output, okay, as an input to suppose say a differentiator. Okay, so this you're passing as an input to suppose say another differentiator. What are you going to get as the output? Okay, and I'll tell you, I'll give you a hint right now. you're gonna get some spikes, and well, actually, yeah, you're gonna get some spikes, and if you're very rigorous about this and want to model it accurately, for this kind of very simple differentiator model, you're gonna have to use the unit step function. But anyways, it's basically some spikes where these vertical regions are, and also do try to do the same thing with sinusoidal wave. Okay, a sinusoidal wave. Take that, take any sinusoidal wave as an input and see what output you get. Okay, I think that one should be pretty obvious. But the interesting thing is well, it's obviously going to be sinusoidal, but you're also going to have a phase shift of 90 degrees. Actually, the phase is going to decrease by 90 degrees if I remember correctly. Yeah, shift to the right, decrease by 90 degrees. So do try that out. And what I'm gonna do here, okay, with this example, we've seen this visually. Let's throw in some numbers. Okay, let's throw in some numbers. Let's say the amplitude, okay, on both ways. Okay, it's 2. Okay, so 2 and 2 here and minus 2 here. Okay, the amplitude for this triangular wave, and let's put in the time intervals. Okay. Well, first thing, I should put the units here since I'm dealing with these numerically now. So let's say this is in volts. Let's say this is in milliseconds. Okay, and also let's put in the time intervals here. So this is 0. This is 2, 4, 6, and this is 8. Okay, and that's 10. Yeah, it really just goes on. So same thing here. At least the time intervals, those are pretty obvious. They're just gonna be the same things here. So I had my the peak was in this vertical region. So this is gonna be 2. This is gonna be 2. Okay. In the middle right here, although it doesn't look like this line segment has doubled the length of this, but it really does. It really should actually, if I were to draw this accurately. So 4 is gonna be here in the middle. There's no discontinuity here. Okay, that's why you don't see something weird here. 6, again, you have your trough here. That's why you have this discontinuity here, and then you have 8. Suppose say here. Okay, 8. So this is also in milliseconds. So this is in milliseconds. All right. The more important thing is what's gonna be my voltage. What's gonna be my amplitude here. I think it's pretty obvious that the pattern is the same here. It's the pattern is a periodic function pattern, exactly the same thing here. But what's the period? Sorry, not what's the wait, sorry, really sorry. What's the amplitude? What's the amplitude of our output? Well, for that we're gonna need to do some calculation. Okay, so suppose say let's take this part for example. Okay, let's take this part for example. What's the slope of that? What's the slope of that? That's basically gonna be your okay. So that's basically gonna be your the derivative of your supply, right? So your derivative of your supply, okay, it's basically the slope, right? It's basically the slope of this graph at any point. I'm choosing this line segment for now. It's the same slope everyone, and the slope is what? Let's see. You have your rise is 2 volts and your run is 2 milliseconds. Okay, so it's your slope or gradient is going to be 2 volts. Okay, divided by 2 times 10 to the minus 3 seconds actually. So milliseconds to seconds. This is gonna be 10. This is gonna be 1,000. It's gonna be 1,000 volts. 1,000. Actually, I'll not put in the units. It's gonna be volts per second. But anyways, we don't need to deal with that. So this is your derivative. Well, but that's not the only thing we need to do. And actually, I haven't thrown in the necessary numbers. Okay. Your capacitance is 0.5 microfarads. Your resistance is 2 kilohms. Okay, your resistance is 2 kilohms. So, again, your question is what's our output? So, the calculation is pretty simple. We just use our formula. So our output voltage, okay, for this segment right here, just for this segment, is gonna be negative resistance which is 2 times 10 to the 3, okay, that's in ohms, and our capacitance which is 0.5 times 10 to the minus 6, and our this is multiplied by this is multiplied by this thing, so and that is 1000. Now I'll just write it as 10 to the 3. I'll write it as 10 to the 3 for the moment. Okay, so this is gonna be equal to if you calculate all this, so this just becomes 1, and all the powers cancel out. You just get a -1 right here. Okay, so for this part, for this line segment, it's -1 volts, right? It's -1 right here. And as I said, this pattern, it's periodic. It's the same pattern over and over again. So your amplitude is really gonna be the same. This is gonna be 1 volts. This is gonna be 1 volts. That's -1 volts. This is in volts, and that's your time. Your time scale, time axis is in milliseconds. So this is basically how your output looks. Okay, for this given input, for this given input waveform, the triangular one, we got this kind of square wave output, right? We were able to express it numerically fairly well. So, all right, so that's done. Okay, that's done. But we have some more things to see. One really interesting thing, I find it really interesting. Okay, this applies to the differentiator and the integrator that we'll see later on towards probably the next video. Is what did we see before? I'll have a hard time scrolling through here and there, but we did see before that your inverting amplifier, if you just make it take more inputs. Okay, this was your inverting amplifier, but you can actually make it take more than one input. Okay, like this, and you'd have your summing amplifier, summing op amp, right? Well, the same thing here actually. And it's all based on the similarity. Based on the fact that your differentiator actually just came from your inverting amplifier. So thing is, if you have multiple input branches, okay, and you feed it multiple inputs, it's gonna behave in the same way. Okay, and I encourage you to actually prove it. Okay, prove the modified formula I'm gonna write by itself. It's pretty easy using superposition. It's really the same thing that we did before. Okay, when we we're trying to prove the summing op amp formula. There are more than one ways to prove that. So what you're gonna have, I can even show it here. Instead of just one of these currents coming in here, suppose say if in this circuit, if you had suppose say a second branch, right here. Okay, suppose that this is V1. Okay, I can no longer call that Vs. So this is V2. And this is C2, this is C1, and I'll just roughly connect this with here. So I think you can see instead of one current right here, okay, as the current entering, the current exiting is the same expression, but the current entering, it's no longer just one current. It's a sum of currents. Okay, so what you're gonna have here, okay, is actually this, right? This plus the same expression for the other branch, right? The same expression for the other branch, and what you're gonna get at the end is basically really just the same thing for as what we got when we are doing the summing op amp formula. You'd have, let's see, V output is gonna equal, it's just the same, it's just the same your response, you could say response, but anyways, your feedback resistance, okay, negative of that multiplied by, okay, the sum of your currents, okay, and here there we had the weighted voltages. Here the equivalent expression is your capacitance multiplied by the derivative of your input voltages. Okay, so C1, as we saw, C1 into the derivative of the corresponding voltage plus C2 derivative of V2. Okay, suppose say if you even had another branch, and we can have as many as we want, as we saw with the summing op amp. So this is basically what happens when you feed it when you feed this in amplifier more than one input. Okay, you have more than one input branches here. Same thing as with this is called I think this name should be pretty intuitive. This is called a summing differentiator. This is called a summing differentiator. Summing differentiator. All right. So pretty fascinating. Let's actually do a problem with this one. Let's actually do a problem with this one. So what I have on hand is let's see. Okay, so we are given two input signals. We're given two input signals. Let's see, we're given V1. Okay, I'll separate this. Okay, so given a V1, and that is, let's see, equal to 0.5 cosine of 5000 t. This is in volts, and we also have a V2. We have another input. Let's see, this is V2, another supply. This is equal to this is a pretty simple expression, 7000 multiplied by t volts. Okay, so these are your two supply signals, and you're gonna feed these to some amplifier circuit, which is gonna give you this output. Okay, which is gonna give you this output. The output is 7.5 sine of let's see, 5000 t. Okay, and actually this whole thing is in brackets. Minus 35 minus, let's see, minus 35 is in volts. All right, so this is your output, these are your inputs. The question is, we just need to find our differentiate, well, actually our amplifier circuit. I have already revealed that's a differentiator. Okay, so we need to find our amplifier circuit. Okay, it's basically a design problem. Now, how do we go about this? It actually looks kind of difficult, especially the problem here. You can again see the fact that your formula is it's supposed to have a negative with each term, or at least it should look, it looks like that based on that general formula, right? Based on this general formula. However, we don't have a negative with all the terms right here. This one is kind of positive per se, and there is no that obvious way to solve this. But we should just go about this methodically. The way to do this is just try to express. First thing, take the derivatives of these and try to express this function right here in terms of the derivatives of these two. So let's try to do that. If V1 is this, what is the derivative of V1? What's the derivative of V1? Let's see. Derivative of V1 is, okay, so you're gonna multiply it by 5000. Cosine gives negative sign, so let's see, negative 2500 sine of 5000, oops, another 0, 5000 t volts, right? 5000 t volts. That's the derivative of this V1. What's the derivative of V2? That's gonna be just 7000, right? So that's just 7000, constant 7000. So derivative of V2, and yeah, the colors are a real mismatch here. But that's 7000. That's 7000 volts. All right. So actually, the units are not volts. I'm again making a mistake on these. It's volts per second, but again, we don't really need to deal with that. So as long as we're doing, dealing with SI units. So as I was saying, let's see. Let's try to express this function in terms of those, right? In terms of those derivatives. So the one that matches with this one, okay, the one that matches with this one is obviously this term, okay, this term. Let's try to factor out the derivative expression from this, okay. Let's try to factor that out from this portion right here. Try to do that. So if we have, you know, 2500, or you could say it's 2.5 times 10 to the minus 10 to the 3, right? 10 to the 3 or 2500, same thing. And you have sine. Okay, actually you should have a negative right here. You should have a negative right here. Okay, should have put that before. You have a sine of 5000t. Sine of 5000t. I did write the negative there, right? Yeah. Okay. Sine of 5000t. This is, I just factored this out from here, but well, it's not done yet. If I factor out 2.5, I'm obviously gonna have a 7.5 outside, right? If I factor out a 2.5, from 7.5, I'm gonna have a 3 outside. What am I even saying? I'll have a 3 outside. And I also factored a negative, as minus 1. I'm gonna have a minus 1 here. Factored a 10 to the 3. I'm going to have a 10 to the minus 3 here. Alright. So, that one's done. And same thing here. I'm going to try to factor out the 7,000 from here. This one's pretty simple. Let's see. If I factor out, let's actually not do that there. Let's actually do this here. If I factor out the 7,000, what I'm going to get is, 35, I factor out to 7, okay, I get a 5, but I also factor out 1,000, there's a negative sign here, same as, the same thing here, okay, I also factor out 1,000, so I'm going to have a 10 to the minus 3 right here. Alright, so, we're pretty much on our way to victory. So this is exactly what we intended, our output voltage function is actually in terms of our derivatives. The derivatives are in supply voltages. These are our derivatives, right? These are our derivatives. Let's replace these by those derivative expressions. So what we have is V output is equal to negative 3 times 10 to the minus 3. 3 times 10 to the minus 3. Let's see. The derivative of this minus 5 times 10 to the minus 3, derivative of this. Alright, pretty cool. Now this, let's compare this with what, if I think you can already see that this should be your differentiator, your summing differentiator, right? Should have mentioned that before. But obviously, how do we know this? We're basically trying to add two derivatives, right? We're trying to take the sum. We're taking derivatives and we are summing them. Okay, taking derivatives and we are summing them. Okay, after maybe amplifying them, as you can see. So obviously, we need the summing differentiator. We need that. And so, for a summing differentiator, where we are gonna have two supplies, the formula is gonna be the general formula. We saw that. It's just you need to write it for two supplies. So this is gonna be negative R into C1 derivative V1 plus C2 derivative of V2. Okay, so just doing a bit of pattern matching, tells us that the ratio of C1 and C2, okay, R negative R is just a constant, okay, and the negative, if we can factor out the negative here, R is just a constant. C1, the ratio of C1 and C2 has to be the ratio of these coefficients, right? The ratio of these coefficients, and that is 3:5, right? That is 3:5. Whoops, not supposed to write that. Equals. That is 3:5. Okay. So, given if we just meet this criteria and given we choose an appropriate resistance, we should have our circuit. Okay. What I'm gonna do is actually pick the resistance, and based on that, we should be able to find our capacitances. A reasonable value for the resistance should be, and I don't know why I'm reverting back to those colors over and over again. Let's choose a strong strong color. Okay, strong color. Thank you. So, okay, so I'm gonna choose 10 kilo ohms. Okay, it seems reasonable, for the ideal of an ideal amplifier circuit and all. So 10 kilo ohms for the resistance. Well, just R. Okay, and based on that, what are these capacitance supposed to be? Well, let's just equate one of these coefficients. So this one has to be equal to this coefficient right here, right? Negative R into C1. So discarding, ignoring the minus sign, R into C1, or 10 times 10 to the 3, R is 10 times 10 to the 3, I can actually write 10 to the 4, okay, into C1, okay, into C1 is gonna equal, let's see, 3 times 10 to the minus 3, 3 times 10 to the minus 3, 3 times 10 to the minus 3, and this is gonna give me a value of C1. Okay, it's gonna give me a value of C1 as 3 times 10 to the minus 7, minus 10 to the minus 7. This is in farads. Okay, but a value like this might as well, it's much better to express this in microfarads, right? So especially hits engineers, so writing these values. So let's see, it's 0.3 microfarads, 0.3 microfarads. But if C1 is 0.3 microfarads, C2 has to be 0.5 microfarads, right? 0.5 microfarads according to that ratio. So now let's draw our circuit. It's pretty interesting. It was a pretty long problem, but we more or less solved it. Okay, so we're gonna have, it's gonna be a summing differentiator. So we're gonna have two inputs right here, an input capacitance, an input, a capacitance, join them. Okay, join them. These are gonna be joined. Let's see, and you're gonna have an op amp right here, This is your inverting, this is your non-inverting. You have your resistance right here. You have your output terminal right here. Let's see. Then you're gonna have your other terminal right here. This is plus, this is minus, this is the output. All right. So now all we need to do is just put in our values. Okay. So let's see. V1 and V2, those were our supply signals. I could write the expressions, but it would just do to write V1 and V2 right here. Okay. So those are our supplies. And what did we see? The resistance we chose as 10 kilo ohms. Chose as 10 kilo ohms. So I'll write 10 kilo ohms here. 10 kilo ohms here. Our capacitances C1, which is the capacitance that's going to be associated with V1, is let's see, 0.3 microfarads. 0.3 microfarads. And C2 is 0.5 microfarads. Voila, we have our summing differentiators amplifier circuit, which given these two inputs is gonna give this output. So it was a pretty fascinating design problem, and we're just about done. Just some things that I need to mention or warn you about. And it's the fact that this really cool amplifier that we just saw, the differentiator, at least the ideal case that we're learning. This is really the simplest model that you can possibly draw for differentiator amplifier. This is the ideal one. Okay? This is actually pretty flawed. Okay, this is actually pretty impractical, and there is a couple of reasons for this. More or less boil down to the same thing actually. Let's just imagine you have your input. Okay, so it's kind of like something like this. Maybe you could imagine as something sinusoidal. Okay, and as real systems, they're not gonna be exactly perfect. Suppose say you're gonna have some noise. Okay, so there's a tiny peak right here. Okay, maybe due to some noise. Okay, some noise, and suppose it then resumes its normal operation. Okay, so what's our output gonna look like? Well, it's gonna be something like this. Well, I'm gonna ignore the negative sign for now in the formula. So, not too weird, not too weird so far. But what's gonna happen here, where we have this noise? What's gonna happen here? Well, if we just zoom into in this part, it looks something like this. It looks something like this, right? It's although it lasts for a really short time, and actually precisely because it lasts for a short time, it's actually pretty steep. It's actually pretty steep. So the derivative is actually really high right here. The derivative in for this noise portion, it changes pretty abruptly, and it's pretty high. So you're gonna have this kind of like abrupt spikes right here. You're gonna have abrupt spikes right here. Okay, so wait, not like that. Let's see. You're gonna have abrupt spikes. You're gonna have abrupt spikes. So, and then it's gonna resume like this. So obviously we really don't want something like this. We really don't want something like this. That's why our that's the main problem of our differentiator. Our ideal differentiator. It's pretty prone to noise. It's pretty prone to noise in the in the supply signal. And again, another thing, and you can actually research more about it. And well, it's pretty simple to see. Just take your sine wave as the supply signal, and keep increasing the frequency. Okay, keep increasing the frequency in the argument portion. You see that obviously your frequency, it's your output is going to be proportional to your frequency. Okay, and yeah, that's the problem. There's really no bound. As long as your frequency increases, your output's going to increase, or at least its magnitude or amplitude. There's no bound on that. There's no restriction on that, and it's pretty bad actually. It's this unrestrained behavior. It's pretty bad. So these are really the imperfections with the ideal differentiator. The practical one, that's more usable. Actually, it's good as a high pass filter and all. Maybe I'll make a video on that someday. But anyways, at least this serves as a foundation. I think it's not exactly some wasted effort. I think it's pretty cool. Definitely, we're gonna look more into these things in the future. But it's pretty fascinating, right? The differentiator. So with that, that's the end of this video.